Well, it's a pleasure to introduce our final speaker, Ed Copeland from Nottingham, on dark energy modelling and testing for it.
Thank you, Anne. Thank you, everyone, for staying. And to the organisers also, thank you for helping me to get here. I arrived yesterday from Chicago, so it's 6 in the morning, so go easy. So this is the basic idea. Just to tell you about the problems. Okay, issues with lambda, issues with dark energy, issues with modified gravity, although Claudia's touched on those. Then testing for dark energy, and finally an idea of hiding lambda, having a Harry Potter invisibility cloak, which shields me from lambda. Let lambda be big, and let's see if we can get a universe that makes sense. Yesterday afternoon, Paul Shellard dropped a bombshell on me. He said he's looking forward to my conference overview. Well, given that I arrived yesterday afternoon and have missed every talk, I did actually pick up 2 talks from Chicago. I picked up George live because I was awake at 3 o'clock in the morning, and David Spergel's talk I picked up after being out for a few glasses of wine with Rocky Kolb and his wife. And then I picked up the public event before my taxi arrived to take me to the airport. So these are my take-home messages from the various 3 talks. If you want a proper conference summary, then you better look elsewhere. Don't use the word crap and Milky Way in the same sentence. One thing I noticed as George did that was the number of viewings went from about, actually it was 7. I'm glad there were 3,000 eventually, Paul, because when I was watching it, there were 7 people watching, and I was one of them. It went from 7 to about 150. And so it made me wonder whether, maybe there really is life out there. As Gaia will solve everything in the Milky Way. George firmly believes the analysis and results of the Planck team. He defended it pretty robustly. Adam Rees thinks George is trying too hard. A new number, I do, so part of this is outreach, right? And I do a fair bit of outreach, and so I do a thing called number file videos. And so a new number has emerged, 217. And not only is it, clearly looks like it's a key Planck number, but it's actually what's known as a Bloom integer, and it's a rare number in that it's both the sum of 2 cubes and the difference of 2 cubes. So. David Spergel seems pretty convinced that Planck and WMAP are consistent than was perhaps initially stated. And with the public talks, it's remarkable how different 3 types of talks to the public can be in their style. They were all good, but all quite different. And finally, I think the detailed interaction and discussion following this, throughout this conference has been ideal, and it's as it should be. I mean, some of these talks were quite technical, and listening, trying to understand, what cleaning the maps meant. And it doesn't look like George likes cleaning very much, but it's been a very good meeting for that, to understand these technical issues. One of the weird things I find, I was thinking about the dark energy, it's one of the few areas that I'm aware of that a Nobel Prize has already gone for a discovery of something we don't understand. We know for the expansion of the universe, and then when you ask, well, what is causing the universe to accelerate, then we don't know. And that's what the essence of many of the talks and presentations have been about. Is it a cosmological constant? Everything looks like it's suggesting it is. Very little evidence of anything deviating from a cosmological constant. But is it an evolving scalar field? Is it the modification of gravity? Is it some aspect of inhomogeneity that we're not yet really picking up on and that we're seeing? Or is it something completely different and yet to be dreamt up? And let me just, one of the bad things about being the last speaker is pretty much everything you've said has already been said. You're going to say has already been said, so I'll shoot through things. But I often hear people say, well, the cosmological constant is, from a Bayesian standpoint, it's the obvious thing to do, right? It's a number. It's perfectly consistent with Einstein's theory of relativity. You just add it in and there's no issue. And so it's just this one parameter that goes into the Bayesian analysis. And yet from a particle physics standpoint, it's a nightmare. And there's a whole load of baggage goes with it. And so to try and understand why it has the value it has. And so how you quite reconcile this one number, which for an astrophysicist you just put in and there it is, and for the particle physicist trying to account for this one number because you believe there's some particle physics input into it, it's anything but trivial to get that. And I think it's worth reminding ourselves, you know, the cosmological constant gravitates. And when you look at the observational value of the energy density that's driving the acceleration today, it's much less than what the theoretical aspect values could be. And that's just as well, because if it was much bigger, we wouldn't be here. The universe would have remained in de situ, and we wouldn't have formed any structures. So, but you can estimate what this vacuum energy should be, and you have the theoretical vacuum comes from some initial bare vacuum, which we don't really know what that's going to be, plus a whole series of contributions, whether it be from 0-point energies of the particles, contributions from phase transitions in the early universe. So if I add up the 0-point energies of the particles, like the leptons, the quarks, and all the gauge fields, then you get some contribution which is dependent upon the cutoff that you have in your theory. And of course, this is one of the reasons why people like supersymmetry, because for every bosonic contribution to the number of degrees of freedom, you've got a fermionic counterpart, and this is what leads to the cancellation of these when supersymmetry holds. But supersymmetry doesn't hold anymore, so there's at least a TeV scale when you're going to have some contribution from the energy density of the particles. And then you've got contributions from phase transitions, whether it be the electroweak transition, maybe transitions occurring at the QCD scale, maybe transitions occurring at the grand unified scale, which will all contribute to this object in such a way that it makes that the observed value that we use, that we see, that's driving this acceleration of the universe, is so much smaller than every other scale that we have, all of which could, in principle, have been driving the dynamics of our universe, and they're not. Why not? So we've seen, just to place things in context, here's the Friedmann equation. Let me just remind you, this is the cosmological constant term, which is the thing that seems to be driving the acceleration of the universe. You've heard a lot throughout the conference about the equation of state. Well, what is the equation of state? It's relating the pressure of the fluid that's dominating the energy density with the energy density itself. So the pressure is related through this equation of state parameter W, and for a vacuum-dominated solution, or a solution that's dominated by a cosmological constant type term, W is -1. One thing that I'll come back to if I have time, is the way we parameterize W. Because if we're trying to test whether or not the cosmological constant is the right way forward, then we've got to allow for things that change with time, because the cosmological constant is constant. That's the hints in the name. And so I've got to be able to parameterize an effective equation of state. And the one that's generically used, it's used in the Planck analysis, is something like this. W is a constant value, so this is -1 today, plus something which is can evolve with the expansion of the universe. But whether or not that's the best way, in particular for things like the Dark Energy Survey, surveys which are trying to look for evidence of evolution, then this is open for debate, I think, and I'll touch on this later. So this is just rewriting the Friedmann equation to remind you that you can of course have the Friedmann equation where the cosmological constant type term can be replaced by something which is evolving in time. And so that allows you then to start thinking about how does things like the Hubble diagram change with an evolving scalar field. So once again, this is a typical way that you parameterize the equation of state. Planck alone provides fairly weak constraints on the equation of state parameter, because there are degeneracies between W and things like the expansion rate of the universe, and you tend to break those by introducing other probes. But once you introduce other probes, as George referred to in his talk, then actually the bounds on the equation of state change. Okay, and this is even assuming, so if I just assume the equation of state is constant, then you can see that depending on what other probes you introduce, you get different sets of values for your best fit values for W. So this is just telling you have to be careful about your priors. As a theorist, looking at the data, you better understand or better be aware of what is being assumed. Okay? This isn't even having any equation, evolution. This is just saying it's constant, and even then you've got quite a wide range of values. One thing that I don't hear people talk about very much, but it seems to me, well, I'm quite interested in it, so I will talk about it, and I'm stood here, is that we will hopefully with things like DES and then Euclid actually be able to seriously probe the region where the acceleration stopped. Right? We have not been in an accelerating universe for the whole of the evolution of the universe. We had to have gone through a matter-dominated period, otherwise we wouldn't be here. So as we go from the matter-dominated to the accelerating period, that's a change. That opens up, in principle, an opportunity to differentiate between models. And just see that change and probe it and understand that change, we will have a way of, hopefully, understanding the difference between models and basically ruling out sets of models and not confirming, but some models will survive and some models won't. So there have been many approaches to dark energy, of course. When you don't understand something, you try everything you can to try and understand its origin. I've tried to describe to you why we don't just simply sit back and say it's a cosmological constant and let's just, get real and just get on with it, and why people have tried lots of things. So there's time-dependent solutions. They generally, the particle cosmologist's favorite tool is a scalar field, and at last we can begin to talk about scalar fields and not feel slightly embarrassed. So we've got time dependence evolving. We can modify gravity, as we heard so eloquently there by Claudia earlier today. We can talk about anthropic arguments, and that's the string landscape for you. We are where we are because without it we wouldn't be here. Perhaps it's general relativity, actually, but the universe is inhomogeneous, and we just haven't yet probed it right to pick up on those inhomogeneities. Then maybe we could do something quite radical. Perhaps the cosmological constant is there. It is big, but we're hiding it. And so I'll touch on that a bit later on. And maybe it's the mechanism's yet to be proposed. It's probably worth reminding ourselves that the evidence for the cosmological constant has been around for a while. Not everyone's taken it that seriously. Back in 1987, on anthropic arguments, Weinberg, in a very famous review of modern physics, a beautiful paper, argued why we should have a cosmological constant and that it shouldn't be zero. And then, of course, as we heard Ofa mentioned, observations of large-scale structure in the 1990s, late 1980s, 1990s, which was showing that standard cold dark matter scenarios were no longer fitting the data. And so I fully concur with that sea change. I mean, when I started my PhD, everything was omega equals 1 standard cold dark matter. Then it began to be clear things were struggling to fit the data. And actually, George, who was PI on the APM data, in 1990 wrote a Nature article where he actually suggested the cosmology is dominated by a cosmological constant with omega less than 0.8. But the subject didn't really take off. It was the reality is the type 1a supernova data is what caused the sea change in terms of how people reacted to the presence of the cosmological constant. So if a cosmological constant is fundamental in some sense, you might say, well, where is it? String theory should be providing me with some mechanism to provide it. And the majority of string theory models are basically supergravity, in terms of cosmology, are basically supergravity models in higher dimensions. We don't really know how to do the full string theory calculations, so we work with the low energy supergravity representations. Gary Gibbons, back in the 1980s, demonstrated the no-go theorem, which suggested you couldn't have de Sitter-like solutions in these models, in other words, it forbade cosmic acceleration. As long as the models, the internal space-time was time-dependent and a compact manifold without boundary. So if you have a no-go theorem, how do you get around a no-go theorem? Well, you violate one of the things that has gone into the no-go theorem, okay? And then you can go. So the typical way that you violate the no-go theorem is that you allow your extra dimensions to vary in time, Okay, these are the radions, these are the size of the extra dimensions, the compact dimensions. So these, by allowing that, you break this no-go theorem, and then you can begin to look for some sort of accelerating scenarios. You want to stabilize them at late times, usually, because these scalar fields coming from the extra dimensions are typically coupled to the important gauge couplings that we have today. Newton's constant can vary if you're not careful, and we know we've got tight constraints on those kind of things. So we need to be able to stabilize them eventually, but we can evolve them. And so this has led to a number of approaches. The brane world setup, which is the one that has led to the idea of the landscape, that's required an uplifting terms in order to achieve the de Sitter solution. The usual, your generic solution to supergravity models is an ADS solution. Okay, the minus pull everything. You have to uplift it to get to a de Sitter solution. So here's your typical ADS minimum. You uplift it with a term, and you can develop a de Sitter solution, which has to be fine-tuned to get the kind of values you want. But once you accept that, then you open up the possibility of having many types of solutions. Because in string theory, where you compactify from 10 down to 4 dimensions, then the internal dimensions are stabilized by the fluxes. And there are many ways of orientating the fluxes in order to stabilize the dimensions. And these are what give you your plethora of vacua. And so the orders of magnitude are 10 to the many hundreds that people talk about. And then you've got a typical separation that would be of order 10 to the minus 500 of the Planck scale. Well, this is like incredibly fine-tuned then. Not fine-tuned, there's a finely grained system. Given that the value of the cosmological constant is like 10 to the minus 118 Planck scales, and the fine grading that's going on here is so much finer, it's fairly straightforward to get to something like that. And so you can argue that this means that there's a mechanism around through some sort of tunneling which will allow me to get to the kind of values that we have today. It seems to me that the problem with this, or if you're happy with the anthropic arguments, it's not a problem, it's a solution. You've solved the cosmological constant, and I think there's a group of people think there isn't now anymore an issue with the cosmological constant. It's just an anthropic argument that we have a vacuum. There are solutions out there, although they haven't been found. The argument is there for their existence. But if you're like me and you don't particularly want to go that way yet, then there isn't one true vacuum, there are many, and it makes it impossible, really, for us to determine which one is the one that corresponds to us. People are trying to put measures on, our previous speaker, Richard's one of those, that's trying to put measures on this landscape. What's the likelihood similar to the type that we have? But it's not, it's an open question still as to how successful this will be. So let me just refer to a couple of other ideas that have emerged. You heard Cliff talk about his own model, which I'll just describe very generally. What's nice about that is that you have a higher dimensional model, right, in which the 4-dimensional cosmological constant, which is the one we're experiencing, at a classical level is cancelled by the presence of curvature in the higher dimensions. Okay, the 2 extra dimensions provide a curvature which cancels out the contribution of the 4-dimensional cosmological constant, giving you classically 0 cosmological constant. And then you generate an effective cosmological constant through loop corrections. That's the basic idea that's going on there, and that's a very nice idea. Okay, now the technical details then have to be worked out, how well it really works. But the idea of managing to cancel out at the classical level to then generate something at the quantum level, I think is a very nice approach. Another idea, which one of the problems we'll discuss in a moment, when you have dynamical dark energy driven by a scalar field, is this scalar field has to be very light. Claudia touched on this. Quintessence models have the same degree of fine-tuning as the cosmological constant problem. Light scalar fields mean fifth force experiments are going to test them and normally rule them out. So you need some sort of screening mechanism. And in the world of particle physics, one way that you can do that naturally is by having something which has got some symmetry associated with it, which forbids that mass scale from coupling in such a way that it can be ruled out by fifth forces. An axion will do that for you, a pseudoscalar which has got derivative couplings there. And there's some very nice ideas of using the axion as not just as a dark matter candidate, but also as a candidate for dark energy. So Kim and Peter Nillis have such an idea where in the world of string theory they've got the possibility of having two axions present, one arising out of the extra dimensions, one which will solve the CP problem, the strong CP problem, and link into dark matter, and then the other which will provide me naturally with a scale of about 10 to the minus 33 electron volts, which is the right scale in order to provide the dark energy, the acceleration that we need in dark energy today. So this is known as the quintessential axion, and I think is one of these which is certainly worth pursuing because it has inherently, because it's a pseudoscalar, this particle or this field has its mass protected. So the idea of having a dynamical evolution of the dark energy goes back has got a long history associated with it now. And the main feature that I think is present that is attractive about it is that you generally have they enter into what are known as tracker regimes, this region 4 here. So the red line here is the dotted line is your background energy density in radiation and matter. That's just dropping off as the universe expands. The n is log of the scale factor. And the energy density is just dropping off. And then you've got the contribution from some scalar field, which is your quintessence field. And the generic idea is it will enter a tracker regime, and then for some reason, something in the potential, it will come to dominate at late. Okay? So entering a tracker regime is quite nice because it means you're less susceptible to the initial conditions. Because you can start the field at another value of its energy density, and it will move along and join onto that tracker. So that's one of the nice things about the idea of slowly rolling fields. It makes the initial conditions less important. But the downside that you have is that you have to fine-tune. So here's just an example. That will give me the type of behavior I require. You can either think about it in terms of the energy density of the field evolving as a function of time, or of the effective equation of state of the field. So what a tracker field will do, it'll mimic the background energy density. It'll just be subdominant, mimic the background energy density, and then come to dominate at late times. So here it means for a while, it's got an equation of state of about a third. That's radiation. It moves into a regime where it's got an equation of state of 0. That's matter. And then at some epoch, it comes to dominate with an equation of state of -1. And the price you pay in all of these, I don't know of a quintessence model that doesn't have this, is that you need to fine-tune because you have to establish the energy density that it has when it comes to dominate, or just below it, and that it dominates within the recent. Usually makes it very small, 10 to the minus 33 electron volts. And so that then means that the fifth force constraints come in. And so a lot of effort has gone into trying to develop scalar field models which avoid those fifth force by, as Claudia talked about, having screening mechanisms. So here are 3 types that are out there in the literature. The chameleon does it by coupling the scalar field to matter in such a way that the effective mass of the field depends upon the local matter density. So in the solar system, the effective mass is very high. That means the field doesn't move very much, so it doesn't produce any long-range interactions. But on cosmological scales, where the effective density is much lower, the field can run free. And then you can experience, it can then act as a quintessence field and drive the acceleration. The k-essence idea are the ones that Claudia was concentrating on, where you have non-canonical kinetic terms present in the theory. You have extra gradient terms, and that can provide a mechanism by which the strong couplings that arrive from having these derivative couplings can become important in the presence of massive sources. And that can be in such a way that it again protects you in local regions and don't play a major role outside of that. And then you have another type, which is a symmetron field, where instead of having coupling, the mass of the field being important, it's the VEV of the field that's important. You have phantom fields, which have an equation of state being less than -1, and I think it's amusing that at the moment the Planck data suggests that. You can have interacting dark energy. Why should dark energy and dark matter be independent of one another? They're not. Maybe they're coupled together. And doing that, you actually then often have a mechanism in which to naturally force the dark energy to start dominating. So if you, for example, you decide to couple the dark energy with the neutrinos, and then ask when does the neutrino mass turn on, then you can do it in such a way that the neutrino mass turns on just as the dark energy becomes important. And so you have a scale, a time, which actually you can justify in terms of why the dark energy is dominating when it is. So you've gotten a way of addressing the coincidence problem. The key thing when you're trying to differentiate between these various approaches isn't just going to be looking at the background dynamics of the field, it's the perturbations, which what Ofa was referring to. And because that's where you're going to get extra information out. And so the coupling of your quintessence field or your chameleon or whatever you have to matter and the associated fluctuations that you get in when you solve Einstein's equations are really important in helping you differentiate between models. And of course, when you're starting to talk about structure formation, you're generally beginning to have to go into nonlinear regimes. And so you need to begin to think about how do you couple them in with large-scale simulations. And this, believe it or not, is only just sort of really taking off. The idea of, it's been around about 2005 or so, Gadget, Springle wrote a code called Gadget, but the idea of introducing modified gravity into there now to also think about large-scale structure with modified gravity has begun over the last 2 or 3 years, and it's a very exciting field. What effects can you get? Well, because these fields interact with standard model particles, then there's inevitably going to be some interaction, even if it's indirect. So light scalar fields that react with these standard model particles will mediate a fifth force. But as I said, we don't see any long-range fifth forces, so we have to have various screening mechanisms present. The dark energy changes the way, for example, that photons propagate through magnetic fields. So a polarized photon can fluctuate into a dark energy particle. You get deviations in the number of photons being emitted and being observed as they go through regions of strong magnetic fields. And so you can begin to ask, how would I test that? And there's some nice paper work done here by actually our chairperson, who's looked for evidence of dark energy through changes in the scattering of luminosities from high energy sources, and looking for evidence of correlations between the polarization and frequency of starlight being emitted. Not surprisingly, as these models are being tested and being pursued, then people now begin to ask, well, do they make sense? They're generally written as classical field theories. What happens if I start seriously thinking about the quantum effects? And so, for example, a recent paper by Claire Burridge and her collaborators have questioned whether or not the classical treatment that we've used in developing the idea of the chameleon field actually is appropriate. And the reason is that the chameleon field couples to the trace of the energy momentum tensor. And in a radiation-dominated era, that vanishes. And that can lead quantum mechanically to rapid particle production. Rapid particle production often means then you're going to have to start taking into account back reaction effects. But you haven't done that at the classical level. And so it's not saying that the chameleon's not working, but it's saying that the framework in which you're doing these calculations may not be the right framework to do. You need to do it as a true quantum system in order to see whether the chameleon actually really is working as you expect it to. We've recently been discussing the idea of probing for some of these chameleons, symmetrons within the laboratory. And so I just thought I'd mention this. So with Ed Hines at Imperial, we're thinking of setting up a system where we basically have a Bose-Einstein condensate, and you separate the condensate. And then you have one of the condensates go to close to a very massive source, and the other one's far away. A chameleon field will change, right? Because you've seen chameleon fields react to the density. So if the chameleon field's propagating through that, it will have a different value close to this massive source than it has close to the condensate, which is in vacua. And then you bring them back and we'll get some interference effects. And so the idea is you try and probe these models through this kind of issue. Well, I'm not going to go into modifying gravity. I mean, you've heard so eloquently earlier today about that, but there are many approaches that have been taken to try and modify gravity. We heard about DGP, we heard about how scalar tensor theory is, Galilean models, massive gravity, and then but on all occasions, you know, we have issues over stability that you have to think about, present theoretical uncertainties, presence of ghosts, instabilities arising due to the presence, for example, in massive gravity. That was what Claire was asking Claudia about at the end of her talk. But it's a very exciting field, and of course that's why we're working in it, because the potential rewards are big. So let me ask the following. What should we do to help determine the nature of dark energy, given we've got these various models? I think we need to properly define the theoretically predicted observables to determine optimum ways to parameterize, for example, the equation of state, so that observers have the best possible chance of seeing any evidence of evolution in that equation of state. We need to start including the ideas of dynamical dark energy, interacting dark matter dark energy scenarios into the numerical simulations. And this is beginning to happen, okay? And maybe we need to start thinking about how do you include gastrophysics and star formation in there. But of course, there's so many uncertainties in that region. It's what Martin Rees would call mud wrestling. And so it's not so clear adding in yet another unknown like the dark energy or some aspects of modified gravity. You're going to glean very much from that because it's already so complicated. On the theoretical side, we want to develop models that go between just our illustrative models. I've tried to give you an idea with extended quintessential axion models, landscape predictions. De Sitter vacuum is basically pretty hard to get in string theory. We need to probe more now this very interesting, exciting area of massive gravity, really test the consistency of it. There are questions about the constraints on the graviton mass itself from loop corrections. Will we be able to ever reconstruct the underlying potential? Will we be able to determine whether or not W is equal to -1? Should we be looking for alternatives, given that the severe constraints that all of these models are under? For example, such as shielding the cosmological constant. So it's a very exciting time with things like the Dark Energy Survey now taking data, and future missions like Euclid, LSST, as well as proposed giant telescopes, let's not forget them, which are going to be coming on stream, like the GMT, ELT, SKA, all traveling in new directions. Here's for you just a little teaser. What do you think is the connection between the remarkable woman, Amy Johnson, and the SKA? I'll leave you, for those of you that have got really bored with what I'm saying, why don't you just have a think about that? So just to reiterate this thing about parameterizing the equation of state, for example, you know, what we've seen that the way it's been done is pretty much this way. It's W of A is some constant plus a function of, if it was 1 minus A times W1. We could instead go for some sort of principal components approach where you can pick out everything, but you need lots and lots of components. Or we could try and do something which allows for. The problem with just having that linear dependence on A is that if you do have something which is a tracker solution, that's rubbish at finding it, okay? Because it's just the constant plus a straight line. And a tracker, you want to be able to see something evolving. And so maybe you need to think of something which has got a little bit more flexibility in it. Or perhaps you should be using something like the energy density and the dark energy itself as a way of probing. And this, I think, this is a recent thing that I've been involved in. And this, I think, is quite interesting because actually it turns out that when you parameterize in terms of the energy density of the dark energy itself, its maximum sensitivity is around Z of order 1/2, which is quite nice if you're trying to look at the turnover from acceleration to deceleration. So let me just finish in the last 2 minutes by motivating the Fab Four. Okay. So we know that in general relativity, the vacuum energy gravitates, and the theoretical estimates suggest that it gravitates too much. The idea here is to hide it, is to say, okay, let the vacuum energy be there. I'm not going to try and cancel it out, you know, by some mechanism to get an effective value of 10 to the minus 3. I'm going to let it be there, and I'm going to hide you from it, hide us from it. So, and I'm going to do it by shielding it with the evolving scalar field. Ofer referred to this, and this is the Horndeski action. It's pretty complicated, but all that we need to see is that it couples the scalar field to various combinations of the curvature. Okay? And what you can do is you can ask the question, is there a self-tuning solution? A solution which, independent of the presence of a cosmological constant, will be the same at late times. And there is. And you can determine the conditions under which it will occur. And this is the condition that long action reduces down to one that has just four potential type terms. And so you can see why. Well, Tony Padilla is a collaborator on here, and he insisted on the Beatles. And now you can just start asking questions about the evolution of this system. You can see the field couples to curvature terms and scalar fields. And you can find solutions which, let me just try and show them to you. The late time solutions are basically flat space. Independent of what's happening to the cosmological constant, this system evolves down to this late time scenario. Of course, this isn't where we want to be. The hope will be that as the system evolves there, it finds a cosmology that we're used to. And so here's an example of it just going through a phase transition. The scale factor, as the system evolves so it's a symmetry breaking phase transition, and the scale factor just keeps on evolving through it. And then the richest scalar, for those of you close by, you can just see a little bump here, and then it goes flat. And you can find solutions that act like stiff fluids, radiation, curvature, and here's an example of one that acts like radiation. Remember, there is no radiation, it's just the combination of these scalar fields, and that it then evolves down. This is the acceleration parameter. It evolves down to flat space at late times. This is a matter-like one. And our hope, and although we haven't done it, we're working with Ruth Gregory on this. Our hope is to try and find a cosmology that makes sense, that then will be an alternative that will give us something that people can go and probe. We haven't got there, and we may not be able to get there. It might not work, but I think it's a neat idea that you have a system that isn't worried about the cosmological constant at late times. It will evolve to some self-tuning solution, and it could be that we have a way then of finding a cosmology with it during it. Horndeski, by the way, went to Amsterdam to a conference. He went to a Van Gogh exhibition and got hooked by it and left physics. And he's now an artist working in Santa Fe. So that's it. So depending on your faith in the idea of the string landscape, you could argue there isn't a cosmological constant problem. It's an anthropic argument, and it's solved. If you don't want that, then you need to understand why the value of the cosmological constant is what it is. And quintessence type approaches require light scalar fields, so we've got to deal with fifth forces, which means we've got to have proper screening mechanisms. And there are a number of ways of doing that. Alternatively, you could try considering modified gravity, which also will bring in with it various screening mechanisms, and such as massive gravity. And this, but as I said, this brings in with it its own constraints. I haven't had time. An area that people are now beginning to work in is to develop the equivalent of the PPN formalism that's used to constrain the solar system, to think about working on generic modifications of Einstein's theory applied to solar system constraints, applying that to the cosmological constraints. And I haven't had time to discuss that today. That's the PPF formalism, and there's a lot of work going into that at the moment. And then finally, I mentioned the Fab Four, which is basically a way of living with a large but changing cosmological constant. And that, even if that in its own right won't work, I think the idea of being able to do that is a very interesting idea. And so there's something in there, there's the seed of a potentially interesting feature. So thank you.
Thank you, Ed. I think there was a typo on one of your transparencies.
Oh, right.
It wasn't Burgess, Davis and Shaw, it's Burridge, Davis and Shaw.
Oh, that was a typo.
I think Burridge might still be here.
Sorry.
So, okay, we've got time for a couple of short questions.
Just a minor point on your discussion of predictions of an acceleration pre-1998 on Larry's behalf. I think it's worth saying that there were a whole bunch of theoretical papers, as I'm sure you know, by people like Lawrence Krauss and Michael Turner and Sean Carroll, and they were mainly motivated by the time span of the expansion. But I think Krauss in particular talks about a jerk between a deceleration and an acceleration, so it's quite prescient, And the only reason I mention it is it feeds into Ofer's talk, because I think when we talk about a paradigm shift, especially to the younger researchers, most of us, we like the word paradigm, but the shift thing is completely wrong in the Kuhnian point of view, because it's always gradual. It's not a step function or anything like it, which is quite important.
Any more questions? Everyone tired? Okay, well, let's thank Ed again. I want to thank all the speakers who've helped make this conference a really great conference. And also, a conference wouldn't be the same without its participants. So thank you very much, all of you, for coming. For those of you who've contributed to our plenary talks, our parallel talks, or who've just contributed to the discussion and the atmosphere. Thank you very much.